Stanford University.
It's a real honor and pleasure to be here to participate in this inaugural symposium of this very exciting institute. I think the place and the time is absolutely right. Stanford has all the expertise to do some really breakthrough things in this space. Before I get started, I want to just sort of truth in advertising. I am not a neuroscientist. I work with neuroscientists. I'm interested in neuroscience, but my core expertise is in materials science. And in particular in electronic materials and device physics, and I'm an engineer. I like widgets and gadgets and so on, and it's really kind of that perspective that new techniques and methodologies and measurement capabilities could be additive and be an important part in trying to decode and understand the function of a complex system like the brain. So with that as background, I'll step you through three different things that we've been pursuing at Illinois over the years that I think could have value or have already demonstrated some value in neuroscience. The first is in soft and conformal electronics for doing high-resolution mapping of electrical activity on the cortical surface. Next is in injectable optoelectronics, ultra miniaturized devices, microfluidic systems that can inject down into the depth of the brain to interact with the brain tissue in advanced ways. And then the third is sort of an exploratory effort that is kind of in the very early phases to give you a sense of where we think there are additional opportunities. So, as a materials scientist and an electronics guy, I think about the brain as, maybe nature's most sophisticated electronic system. And if one wants to do studies of the brain or you want to perform therapies on the brain, it might be useful to be able to bring to bear on that problem man's most sophisticated electronic system, and that is the digital integrated circuit, which in its present form is highly mismatched to the soft textures and surfaces of the brain. So it's a spectacular piece of technology, but it really wasn't designed to integrate with biology in any useful way. The geometry mismatch is obvious, but it's also a mechanics mismatch as well. Silicon has a modulus of about 150 gigapascals, and brain tissue, as you know, has a modulus around 5 kilopascals. So huge differences here. And the question is, how do you span the gap to enable a useful level of integration of this technology with biology? And this is kind of the workhorse way that it's been done, as many of you know, over the last 15, 20 years. And it's the concept really is that you establish the interface by creating sharp pins of electrodes built around etched features in silicon that terminate at a flat platform. So you can take a piece of electronics out of this wafer, mount it on that flat platform, and then you do integration with the brain by just inserting this device into the surface of the brain, and these pins can penetrate to different depths and accommodate the geometry mismatch. But it doesn't really do anything about the mechanics mismatch. So you have essentially rigid needles of material in a piece of jello that is time dynamic. So it's pulsating, it's swelling, it's deswelling, it's rattling around in the intracranial space, and so that creates irritation over time and degrades the quality of the electrical contact, which is a clearly non-ideal thing. The other aspect of this is you can do contact over small areas, but you certainly couldn't map the entire surface of the brain. And so this will remain a very powerful workhorse tool for the community into the future. But from my vantage, it might be interesting to contemplate materials approaches that allow you to take this full thing and melt it into the surface of the brain so that it could interact with the gyral surfaces as well as the sulci all around the outside surface of the brain, and maybe provide sampling and simulation capability at the level of, say, 100 million stimulation and measurement points. And so that's the future that we would like to enable. It's like, how do you create electronics that are soft and shape conformal and that look a lot more like biology? How do you do that? And that's a topic that we've been working on for a long time. And this talk is about neuroscience, so I'm not going to tell you all the details about how you actually go about doing that, but just make the claim that it is, in fact, possible to build a piece of silicon electronics that can integrate with that kind of surface. And it really relies on two pretty simple ideas, and then lots of engineering elaborations on top of those two concepts. And the first one is that although silicon is in fact a high modulus rigid material, it only has those properties when it is in the form of a wafer, because the bending stiffness is proportional to the cube of the piece of material that you have. And so you can make silicon flexible and floppy just simply by making it thin. And you can exploit that cubic power of the dependence of the bending stiffness on thickness to create pieces of silicon that can really flop around and bend a very sharp radius of curvature and have very low flexural rigidity by making very thin. So it turns out there are ways to take a silicon wafer and shave off of its surface very, very thin membranes or platelets or wires, or in this case, ribbons of device-grade silicon. And so that's a step in the right direction. It's still not good enough, though, because if you have a piece of material that can simply bend, then you can wrap things like sharp edges or cones or cylinders, but you cannot wrap a complex surface like that of the brain. You need something that not only bends, but also stretches like a rubber band. And so that challenge can be addressed with the second simple concept, which is if you have this flexible silicon, you can take that and you can bond it to an underlying soft elastomer material, and you can bond it in a wavy configuration like this. And so in this way, you've created a hard, soft composite material where the mechanics is dominated by the soft substrate. The electronic function is provided by the silicon, and the integrated system can accommodate large strain deformations, because as I stretch this thing out, the geometries of these wave structures can change to accommodate that overall deformation without reaching fracture thresholds in the silicon, which is about 1% tensile strain. So it's essentially like an accordion bellows is the way you can think about it. And if you do this kind of integration, you have the ability to build silicon electronics that can be stretched or twisted or folded or deformed in pretty much any way that you want. So that's the concepts just illustrated in the form of strips of silicon. That's not an integrated circuit, obviously, but there are ways to go from these ideas to things that offer the functionality of a state-of-the-art integrated circuit that you would normally find in a rigid planar format on a semiconductor wafer. So those are the ideas. Here's an example of a system built around those ideas that provides unique capabilities in neuroscience. It's an array of electrodes. It's essentially a micro ECOG device that has the ability to flex and fold and conform to the surfaces of the brain. The key feature is that because we can integrate electronics into this system, we can reduce dramatically the number of wires that are needed to do readout across the array. And so you use multiplexing strategies similar to those that are used in high-resolution displays to do large electrode count integrated mapping systems with very small numbers of output wires to do the measurement or the stimulation. So in this particular case, you have 360 electrodes. It's about a 500 micron pitch, and we only need about 39 wires to do the full readout. So that's the entire system. If you look at the structure in detail, you see platinum electrodes here. This is an individual unit cell in the overall mapping array. And that unit cell consists of two transistors built on this ultra-thin silicon. One of those transistors acts as a multiplexer, the other one as a buffer, which is connected to the input, which then connects to this flat pad of platinum to establish a low impedance interface to the subdural surface of the brain. And then that's all wired up in an overall grid array to allow high-speed readout over large areas at a high pixel count. Because of the mechanics ideas I described to you before, this system offers not only wafer scale levels of electronic performance and ability to do multiplexing and also local signal amplification to the extent that that's necessary, but you can really fold it and roll it up in unique ways. So this is an example of a device where we actually created an open mesh geometry to enhance the mechanical properties. You can sort of roll it up into a cylinder like that. You can also wrap it around a sharp edge and then use this as a device to probe not only the gyral surfaces but also into the interhemispheric fissure or down into the individual sulci to do high-resolution mapping of hidden surfaces in ways that would be very difficult or impossible with other approaches. So this is a picture of one of these devices inserted into the region between the right and left hemispheres of a feline model. This is done in collaboration with folks at the Epilepsy Epilepsy Center at University of Pennsylvania's Medical School. You can also mount these just on the surface of the brain, again, feline model, and then do mapping, at high spatial and temporal resolution to look at different forms of brain activity. Let me show you one example. This is the mapping of a seizure event that's induced by applying a picotoxin right to the surface of the brain at the edge of one of these mapping arrays. So this is about 1 centimeter by 1 centimeter, almost 400 channels. And just to establish a point of reference, this is a clinical ECOG array that's used in diagnostics for surgical procedures that are used to treat acute forms of epilepsy. And we're doing 390 individual point measurements across that area. So let me show you a movie of what this looks like in slowed down time. Let me see if I can reduce time. So what's shown here at the bottom is an integrated trace corresponding to the electrical activity measured over the entire area. The picotoxin is induced at this moment. This is time in seconds. And what you see is there's a behavior of electrical activity that you see at this coarse resolution, but at finer resolution enabled by these kinds of arrays, you can see there are elaborate plane waves and spiral wave instabilities associated with the seizure. So the picotoxin is introduced here. The physical seizure doesn't happen until about 1.5 seconds later. And the physical seizure corresponds to this very time periodic variation in the overall potential, and that's reflected in this recurring counterclockwise spiral wave instability that happens over and over again, in this case 19 repeating cycles, eventually terminated by a plane wave disturbance as well. So this kind of data can provide new insights into the electrophysiology associated with seizures, but in a practical clinical standpoint, it provides a very high resolution way to map the electrical activity of the surface of a brain of an epileptic patient to enable a more precise assessment of which regions of the brain to resect to eliminate that kind of disorder. But if we look at this more carefully, you can see at this individual trace, this initial spike associated with the introduction of the picotoxin creates a plane wave disturbance across the array, as I showed. That is immediately followed by a clockwise spiral instability that goes for 3 cycles. There's another plane wave that happens subsequently. You can see it here, corresponding to that individual event. And then you have 19 recurring counterclockwise spiral wave instabilities that dominates the overall behavior, concluding with a plane wave that sort of annihilates those spiral wave type patterns. And a lot of this kind of behavior is reminiscent of what appears in arrhythmias associated with cardiac behavior, and so there may be some similarities there in terms of the underlying physiology. So that's one example. Another way you can use these devices is in brain-computer interfaces, and probably one of the most notable clinical successes of that kind of technology is in cochlear implants, where you electrically stimulate the ear to create a sensation of hearing. And so the concept here would be perhaps with these very high resolution arrays, you could stimulate directly the auditory cortex and eliminate the role of the ear entirely. And this is a higher density version of what I just showed you. It's about 4 times higher density. It's about a 250 micron pitch, but the same overall structural layout in terms of the electronics and the multiplexing. So this is another 300 channel system with only about 30 input wires needed in order to do the readout. And these are examples that correlate the ECOG measurement performed with that kind of device with intrinsic optical imaging, which essentially reflects blood perfusion and metabolic activity on the surface of the brain, in which the animal, in this case a rat model, is being presented with different tonal sounds in terms of blips with different frequencies. And you can map out the best frequency, the strongest response in the different regions of the brain to different audio frequencies. And you can map that out using optical approaches, and that's what's shown here. This is the primary auditory cortex here. This is the ventral auditory field and the anterior auditory field over here. If you look at the overall optical map as illustrated here, it's quite similar to what you see in these multiplexed electronic devices. The key difference here is that the speed with which you can acquire that map is orders of magnitude faster with the electronic approach compared to the optical imaging approach. Only 10 seconds or so required to develop that entire map. And so because I'm a device guy, I brought devices, and I will pass those around, and so you can take a look at these. This is one of these mapping arrays. You can see the flexible electronics there, and move the magnifying glass in place to get a closer view. So that's flexible electronics. It turns out that the same concepts in underlying mechanics and material science allow you to do all kinds of different semiconductor devices, not just transistors and integrated circuits, but optoelectronics as well. So you can create ultra-miniaturized, very, very thin, flexible LEDs using the most high-performance materials available for that class of device, in this case, indium gallium nitride. So these devices are about a factor of 1,000 or 10,000 times smaller than what you can get commercially in a volumetric sense. And what that allows you to do is put these devices on plastic sheets, for example, and bend them. And so you can imagine conforming these to the surface of the brain as well. And there would be interesting things you could do in terms of optogenetics or even spectroscopic assessment of brain activity with that kind of technology. But we were more interested in going not only to LEDs, but into devices that mount not only on the surface of the brain, but devices that penetrate down into the depth of the brain. The idea being that you can only determine and do so much if you're confined to the surface of the brain. Being able to get down into the depth will allow you to do other things of interest. And here we collaborated with people at Washington University to bring to bear some of these ideas in material science in the field of optogenetics, which has its origins, of course, here at Stanford University. So I don't have to tell you how this works, but it offers a level of genetic control and cellular level specificity on excitation and inhibition that is unavailable in traditional electrical stimulation approach. So very, very powerful technique. And the neuroscience that comes out of this is extremely important and fundamental in nature, and a lot of very smart people have worked on this. But like if you look at the engineering embodiment of the devices, it's not that great, quite frankly. And it's pretty, from the standpoint of an engineer like myself anyway. So it's like the simplest thing imaginable. Like, you want to introduce light into the brain. Well, yeah, grab a fiber optic and just stick it down there, and it kind of works, and that's fine. But like if you're interested in studying complex behaviors, it would be nice not to have this tether, which could disrupt those behaviors and prevent, studies of complex social interactions or motions in a complex 3D environment. I mean, those kinds of studies might be constrained by this sort of engineering embodiment. So as our attempt to sort of contribute to this community, we begin to look at using these ultra tiny LEDs, mounting them on not sheets now, but thin polymer filaments that could be introduced directly down into the depth of the brain. So we can make LEDs now that have dimensions that are comparable to those of an individual cell. But at the same time, they offer very high performance operations, just a few microns thick, and we can make them as small as you want them in terms of their lateral geometry. So just to set the scale, this is one of these LEDs sitting on top of a conventional fiber optic cable, which is just a big cylinder of glass. It's rigid. It's large in diameter, obviously, and it just does a lot of tissue disruption during insertion. So you can take these devices, you can put them on very thin plastic supports, shape them in the form of a needle, and make entire systems that are only a few microns thick. And because they're so thin, you don't have to stop just with the LEDs, but you can make multifunctional systems. So in a different layer, you can incorporate a silicon PN junction diode, photodiode, so you measure and monitor exactly how much light is coming out. You can introduce a platinum microelectrode for measuring electrical behavior. You can introduce a heater, which will also simultaneously serve as a high-precision temperature sensor. And the base layer, stack those all up together. Now you have an integrated multifunctional optoelectronic device that's still only about 20 microns in thickness. In some ways that's good because it minimizes the tissue disruption during insertion, But as I mentioned to you before, as things get very thin, their bending rigidity goes down. And so these are actually, even in that fully integrated form, too thin to allow penetration into the brain tissue. So what we do to avoid that problem is we mount this system on a temporary injection microneedle made out of a thicker polymer shaped into the identical geometry and bonded to this multifunctional system with a bioresorbable adhesive, in this case silk fibrin, which will dissolve in cerebrospinal fluid. So if you take those kinds of systems, you can inject them down in the brain. This is a picture, though, of one of these devices, just to give you a sense of it. So it's threaded through the eye of a sewing needle. And then the needle sort of wrapped around. You can tie this thing in a knot, but there's 4 very tiny LEDs there, and I have one of these devices as well. Pass it around. You can see the blue light. The individual LEDs are too small to distinguish individually, but they're there, and they can be configured to be independently addressable as well. So this is what it looks like injecting down into the brain of a mouse. That is configured to offer this kind of optogenetic capability. So we use the same fixtures for doing the injection as you would otherwise use for optical fiber. You inject it down. In this case, we introduce some artificial cerebrospinal fluid to accelerate the dissolution of that silk layer. Once it's dissolved, we pull the injection needle back out, and that just leaves embedded down into the brain this multifunctional LED system. Because it's small, it has reduced gliosis, reduced neuronal damage, reduced immune response compared to fiber optics, certainly compared to metal cannula, and we can see the effects even of that microneedle. If you leave it in, you have a lot of adverse response. You pull it out, and that largely disappears. So thin and flexible is extremely important for biocompatibility at this level. Now, if you think about it, though, it's sort of a scary situation because now you have a light bulb embedded in the brain. And like, what do you do about the heat? And that is something we thought very deeply about before getting involved with the animals, because the brain can only tolerate about a degree of temperature increase before it leads, you induce cell death. So how in the world can you have an LED operating in the brain without causing damage? And it turns out there's sort of 3 things that allow this to happen. One is that the LEDs themselves are so small, the surface area to volume ratio is huge, and that allows for very fast rates of passive thermal diffusion. So heat is traveling away from these devices very efficiently. Number 2 is that the brain is a living system, and so the blood flow and the vasculature acts as essentially a liquid heat sink, pulling heat away from the devices. And then the third aspect is that for optogenetic stimulation of this type, you only have to run the LEDs in a very low duty cycle mode. So it's millisecond type pulses at a few hertz. So we've done this in a systematic, quantitative way. We looked at operation of these LEDs in brain slices, explanted brains, and then in living brains using those integrated temperature sensors to measure the change in temperature at the position of the LEDs. And what you see is that the temperature rise, even when you're running at the highest repetition rates, are only about 1/10 of a degree, 10 times lower than the damage threshold. So the solid lines here are data. The dashed lines here are full 3D finite element models of the heat flow, in which we've used the lowest frequency data to fit the constitutive properties and then fix those properties with no free parameters to match the experimental data at other frequencies. So if that's the LEDs, how do you power them? And the way that we decided to do that is to use RF harvesting, because that provides a wireless way to turn the LEDs on and off and also deliver power to them. So this is a 900 megahertz power harvester, and it plugs into a releasable receptacle here that connects electrically down to the LEDs themselves. So the mice sort of look like this when all is said and done, and so they sort of wear around this hat, and that allows you to turn the LEDs on and off. And this works, so you can do all the standard optogenetics experiments, and we've demonstrated that, but without the tether, without the external light source, without the fiber optic. And this is just a standard example, one of the first demonstrations from Carl's lab of training place preferences by using optogenetics to optically stimulate the release of dopamine, the creation of a pleasure response in the animal. You can train the animal by turning the LEDs on whenever they're in this region of this Y maze to like that part of their environment more than any other place. So this is untrained. They like to stay at the corners here. If you train them, then even without optogenetic stimulation, they like to stay in that part of their world. So this demonstrates that it can work. But if you're doing research in this area, the goal is not to do a hero demonstration, publish it in Science, and then go on to the next thing. It's really to establish some kind of capabilities that can be broadly used by neuroscientists. And so over the last year or so, we've been contacted by dozens of optogenetics groups that would like to have access to these kinds of implantable LEDs and the wireless control systems. The devices that I passed around a few moments ago were fabricated in very advanced techniques by graduate students, but over the last 9 months, we've worked closely with external vendors to establish a manufacturing flow for these classes of devices, and we've been able to do that. And so you can build these things for almost negligible cost, just about 50 cents each. And so you can imagine using these things as a disposable component of an optogenetics research program. We're gearing up to just give these away to the community. Should be available in a few weeks. So I'll pass around an example of one of these devices in one of the boxes, and then one of the devices sort of freestanding so you can hold it, but don't worry about it. It's cheap, so if it breaks, we're not that concerned. Not the black box. You can keep the other one if you want it. So that's one thing you could do. The other thing you could do is you could dramatically reduce the size of these devices. So having this head stage is one thing, but if you move to 2.4 gigahertz and you reduce the size of the antenna, you can make the entire harvester in this size scale, which allows you to do complete implantation. So the mice that have these LEDs in their brains with the RF control look exactly like regular mice. The other thing you can do is you can use this as a platform for doing other things, like outside of the area of optogenetics. You can actually introduce microfluidic channels, controlled pumping schemes that allow you to draw fluid up from the brain or inject drugs down into the brain. You can co-integrate that microfluidic capability with UV LEDs, for example, to do photoactivation, uncaging of drugs. Lots of possibilities, and this is just giving you an example of some of the things that we're working on now. But to conclude, let me move into a different topic area. So I think those two programs, surface-mounted electrodes and electronics, that is, and injectable electronics, those appear to be straightforward, and you can expand on them. The other challenge that I don't think we have a fully developed solution to yet, but I just described something that we've been thinking about, is just a recognition, as Carl's recent paper here demonstrates. There's just incredible 3D structure associated, with the brain, as everybody here knows. And so you have all these filamentary, structures and loops and so on, and it's in the full 3D depth. And so, like from a materials standpoint, how do you address that level of complexity? And how do you get electronics to interact with that 3D volumetric structure beyond just an individual penetrating pin? And the problem really comes back to the nature of electronics as we know it today. It's essentially a planar system. You can make that into a flexible and stretchable technology, as I described before, but essentially it's still planar. Like, how can you go from this kind of thing to filamentary structures of active electronics that would raise up out of the plane of that piece of electronics to allow interaction with the full 3D volume of the brain? That's something we've been thinking about for a number of years. How can you create sort of a silicon electronic fuzz or a mesoscale network that would come out of the plane without throwing away any of the knowledge base or the technical sophistication associated with silicon CMOS electronics? Like, how do you do that? And so we think we know how to do it, but this is ongoing. So let me just kind of conclude with this to give you a sense of stuff that may be coming in terms of future capabilities. So here's how you do it. So if you want to make something that's 3D, it still needs to have this flexible sort of conformal nature. So you need to use an elastomer substrate. But you don't just use the elastomer in its undeformed state. You take it and you stretch it. So you might stretch it by 400%. So the extreme stretching. And then what you do is you create these freestanding ribbons using these etching techniques that I alluded to at the beginning of my talk. But you control the surface chemistry so that when you create those ribbons and transfer them to this pre-stretched silicone substrate, they will spontaneously, covalently bond at specific lithographically defined points that I'm indicating here with red dots. So if you do that, it's bonded only at these locations so that when you release the pre-strain, the silicone rubber substrate goes back to its original dimensions, and when it does that, it places this overall structure in a state of compressive stress. At a certain stress, you will exceed the threshold associated with a non-specific van der Waals bonding in the regions between these red dots, and that will create an out-of-plane deformation and delamination up and away from the surface of the substrate to create a 3D structure. This is a movie of how that happens in a very simple case. I'll show you a much more complex case in a second, of a filamentary serpentine that spontaneously transforms into a 3D mesoscale conical helix, as shown here. So there's a side view, top view, front view, and kind of 3D view here. And so you can see you go from planar to 3D in that way. Here's an example of what it looks like, full 3D finite element modeling of these kind of conical coils bonded at specific locations to the underlying released silicone substrate. There's a colorized SEM view. That's device-grade monocrystalline silicon in the form of a conical helix. So that concept can be used for many, many different geometries. So you can imagine all these different kinds of building blocks. Here, this is the 2D geometry. The red dots correspond to the bonding points. And this is the 3D structure that results from that release of pre-strain. All kinds of stuff, you know, like rotated tables, butterflies, tilted tables, flowers, inverted flowers, two-layer flowers, all kinds of stuff. You can even induce hierarchical buckling to create even further extension out of the plane. So here's an example of that. Buckle up once, and then another structure buckles on top of that. So you push the silicon even further away from the originally sort of 2D surface where it was located. Here's another example, buckle again. Here's a 3-level structure, buckle once, buckle twice, buckle 3 times. This actually has larger extent out of the plane than it does lateral extent over the geometry. This one's interesting because it gets to something that's at least reminiscent of the kind of 3D, you know, filamentary networks that you see in the brain. This is 2 serpentine structures at right angles bonded in the locations indicated by the red dots there. You form this kind of 3D system. And here's what it looks like when you form that. So this is finite element modeling, planar. Now it's moving up out of the plane into a fully interconnected silicon structure that can easily be populated with high-quality electronics. This is what it looks like experimentally. On a side view optical micrograph, this is the theory. It's a very good correspondence there. This is the final view graph for my talk, and it's just a delightful, at least from my standpoint, a cool structure of silicon. You know, who knew you could make silicon look like that? But anyway, you can do this, and it's fully compatible with integrated circuits. So now you can imagine launching very high-quality electronics up out into a 3D space, and I think that'll be an interesting starting point for some of our future work. So with that, let me just conclude. I'll come back to the 3 topic areas I told you about at the beginning. Soft conformal electronics, we're using that for these ECOG devices. Injectable optoelectronics, microfluidics is a little bit newer, but that's straightforward. I think these are emerging technical opportunities that are very clearly defined, and we plan to drive a bus right through those. This is a little bit more nebulous, but I think it's interesting, and you know, it will lead to something valuable, hopefully, for the neuroscience community. So I think all of this stuff really you know, has foundations in the science of materials and device physics, but you know, with a trajectory that's oriented toward development of new technologies for neuroscience and this type of community. We're very interested in doing things that are relevant at that level. So the work is highly interdisciplinary, as you might imagine. So we work with theoretical mechanicians, manufacturing guys, 3-5 semiconductor growth guys, surface chemists, and then, you know, folks in the neuroscience community, optogenetics, epilepsy, brain-machine interfaces. Those guys are important. The most important folks, though, are the students who do the work. I just get to talk about it. They actually do it, come up with a lot of the best ideas. I've been very fortunate to have outstanding graduate students and postdocs over the years. So with that, I'd like to thank them and thank you for your attention.
For more, please visit us at stanford.edu.